Okay, let me start. So today we are going to discuss about finite cellular automata. So since we are talking now finite cellular automata, so there should be infinite cellular automata. However, cellular automata defined over infinite lattice. So classically, cellular automata infinite. They are infinite in that sense. Well, let us revisit again the definition of a cellular automaton. I have slightly changed the definition. You may notice here that here I have written a cellular automaton is a quadruple LSMR, where L is a d-dimensional lattice. See, in the classical definition, we don't write L, rather we write directly z to the power L. Right here I have written instead of z to the power d, I have written L. Obviously, L is subset of z to the power d, and L is a d-dimensional lattice. And the rest things are same. S is a finite set of states, M is a neighborhood vector, and R is a transition function called room. These things are same. So only edit I have done here. That is, while I'm defining this lattice, I have represented that by L, which is subset of z to the power d. With this definition, I can go to the definition of finite cellular automata. A cellular automaton is finite if L is finite. That is, if the lattice is finite, right? Then the cellular automata, the cellular automaton is also finite. Now, what does it mean, this finiteness? It has several implications. Firstly, we have discussed that before L L has to, L forms a lattice, and to form a lattice, that L is to be additive subgroup. So two properties were there, right? To be a lattice, one is subgroup property. So L is to be sub-additive subgroup of, say, it was R to the power D. Here, L is to be additive subgroup of Z to the power D. Okay. And the second point is, as usual, it is a discreteness. So therefore, since I'm defining a cellular automaton, and since the first one is the lattice, so it is to be a finite and it's to be lattice. So both the properties are to be satisfied. Now this is an exercise. So you take a finite L, right, and test if that finite L can form a lattice. Okay. See, recall that how we have done it. In the previous case, we have considered, this L, okay, or z to the power d, that is actually infinite set, right? So this is not infinite set here. So just a sec, just a sec. Sorry. Sorry. So mm, in the previous case, it was z to the power d, and that formed a lattice because it was additive subgroup, and addition was closed in that case. But if I take a finite subset of z to the power d, will it be closed? Right? So that is a major issue here. So you test, you do it. I can give one example just to help you, to help the precise. Consider a set of integers. Say, let us call it Zn. Say it is actually 0, 1, up to n minus 1. So it's actually set of uh, n natural numbers, right? 0, 1, 2, etc. Okay. This is sometimes called as a set of integers modulo n, right? So, and it is a notation. So, who have studied group theory, you know this, the meaning of this. So, Zn, I want to mean here, it is, a set of integers under modulo n operation, right? So, suppose, so in this case, in this set, what is the addition here? So, addition, this is modulo n operation, right? Now, question is, does this set form a group under addition? So, firstly, it is closed. The question just now I have raised, that is it closed? To be a subgroup or to be a group, first is the closed net. So, if you add two elements, the addition, the result should be another element of that set. That is the meaning of closeness, the closure. So here, if I apply the modulo n operation, you take any two elements, any x and any one, and do addition, and then do modulo n, and you will see, understand that the after addition, the elements will be in Zn, so it is closed. So what is the second property? Second property of a group is associativity. So it is always associative. X plus y plus z equal to x plus y plus z. So this is the property of associativity. So property of associativity property is the property of addition. So there is no problem. Third property is to be a group, you should have an identity element, and in 0 is here. So 0 is an identity element, and finally it has to have inverse, right? It has to have inverse. So what is the meaning of inverse? X is say inverse of y. If x plus y equal to 0, right? And since it is modulo n addition is modulo n operation, so you can find always two elements, addition of which is 0, right? So for example, 1 plus n minus 1 is equal to n is equal to 0 because it is modulo n operation. So inverse also present here. So now, if this is addition modulo n, then it forms a group. So it's additive group. Now, since Zn is subset of Z, right? So Zn is an additive subgroup, right? So from the definition of lattice, first one is it has to be subgroup, then has to be discrete. Second point is always satisfied in this case because I have taken Z to the power d. Okay, so and I'm saying if I take Zn, it also forms a subgroup, right? So here, as I've said, Zn forms a group, and so it's a subgroup, so it's a lattice. So if I take this one, it will form a lattice. So we take this set in general. When you specify n, we take this set, right? And in our further discussion, when we shall discuss about finite cellular automata, then our set, this set, the lattice, consists of these elements 0, 1, 2, n minus 1. Right? So now is an exercise with this hint. You check whether you take a finite L and then check whether it forms a lattice or not. Anyway, so it forms a lattice, at least for one dimensional case. I will give an example. And the lattice is finite. Since it is finite, the lattice should have some boundary, right? Since you have finitely many cells, it will have boundary. The cells, there's some end cell, start cell, end cell, you can find these kind of things. So therefore, you need to specify boundary condition. This kind of boundary condition was not present in case of classical cellular automata. Why? Because why it was so? Because we have defined the CA over an infinite lattice. It was z to the power d. Since it is not infinite, so you have to specify the boundary condition, and it is the important one in case of finite CA. So next we are moving to boundary condition. For finite CA, there are two popular boundary conditions. One is open boundary condition, another is periodic boundary condition. Now, what is open boundary condition? Open boundary condition, is something. It will have some missing cells. Okay, only you have finitely many cells, and when the end, I mean, you'll not find any more cells. It is open. Now, if it is open, then the main question is, in case of boundary condition, main question is, what are the neighbors of boundary cells? Right? In case of finite CA, there will be always some cells will miss some neighbors. You have defined some neighborhood vector, right? To be a CA, you need some neighbors. And since your lattice is finite, there will be some cells will miss some cells. And in case of open boundary condition, and it says that missing neighbors of cells assume some specific states. Let us take example. So 2D case. Suppose it's a 2D CA, 2D grid, and this much cells are there. And suppose in my state set, the states are 0, 1, 2, etc. These are the states. And suppose I am assigning this one 0. 0 means what does it indicate here? That in the boundary cells, the left side of the left boundary, leftmost cell. So consider the first cell in the figure, right? The first cell in the figure. The left neighbor, it doesn't have a left neighbor, right? So now when it will find its next configuration, next state, so it has to consider the states of its neighbors, but all neighbors are not present. Then how it can work? So then what it does under this condition, it assumes that the missing neighbors, it first assumes, okay, it is having all the neighbors, but who would exist? It assumes that their state is always 0. Instead of 0, you can assign another state, say 1. So if your state is something different other than 0, 1, 2, so that specific state is assigned to these missing cells. So this is open neighbor cell. So, so uh, just a second. Okay, sorry. Okay. So, as I've said, that instead of state 0, it can have any other state. Okay. So, in literature, when we talk about null boundary condition, uh, sorry, when to talk about open boundary condition, we find that most of the works they consider 0 as the state of their missing neighbors, and so this kind of boundary is a special name called null boundary condition. Okay, so actually, what is the meaning of this? What is the meaning of this null boundary condition? It means that suppose in the state set you have 0, 1, 2. Okay, then the missing neighbors, missing cells actually, they assume they are. It is assumed that they are always in state 0, right? In case of 1 DCA, it may look like this one. In the figure, there is a mistake. I've taken somewhere else, so I didn't modify it. But so it will cell 0, okay? Because cell 0, cell 1, etc. Because in my definition, it doesn't start from cell 0. It can't start from cell 1. It starts always from cell 0. Okay. Anyway, if there are n cells and this it looks like this one. So this kind of boundary condition is called null boundary condition. Okay. In case of open boundary condition, so it means is boundary is open. In that specified part, I can think that. So different kind of states being assumed by the boundary cells. I mean, different kind of states of the missing cells are assumed binary cell. Although in case of open boundary condition, most popular thing is fixed state. Fixed boundary condition means you assign some fixed state to the missing cells. But there are some works, some authors, sometimes some variable states, are considered. Suppose time to time the state of missing neighbors will change. That is also considered. Okay, so there are several options of this open boundary condition. Next one is periodic boundary condition. In case of periodic boundary condition, the lattice actually is considered spatially periodic. Okay, it is spatially periodic. So, for example, for one-dimensional say cells form a circular array, right? So, what does it mean? Take an example of one boundary case is like this. So, in an array of n cells, cell 1, cell 2, cell n, and then after cell n, second cell 1 comes, right? So it forms a circular array. Therefore, the last cell here in this case, it assumes that its next right neighbor is the first cell. Similarly, the first cell, it assumes that its left neighbor is the rightmost cell. So win this way. Okay. So you can consider that it's again an infinite lattice, but it's periodic, spatially periodic. Okay. So its name is periodic boundary condition. Recall that in last class we were discussing about periodic configurations. Similar concept, right? What was the periodic boundary condition? A small, what was the periodic configuration? A small configuration repeated over the lattice, right? And I've also said during that discussion that if you can know the small part by repeating that small part everywhere, you can get the whole configuration, right? So similar thing is periodic boundary condition. So it's here it is finite, C is finite, but I can think that okay, I will repeat that finite part over the infinite lattice, right? So actually, this periodic boundary condition is equivalent to periodic configurations, right? So, if we want to deal with periodic configurations, we need not to consider infinite lattice. We can work with finite lattice, and then you assume that periodic boundary condition, and will evolve the CA over that in a finite lattice. And since time to time I can get the configuration of the small part of the finite part by repeating that finite part over the whole lattice, I can get the full configuration, right? So periodic boundary configuration condition is equivalent to periodic configurations. So these are two popular boundary conditions. One is open, another is periodic. In the CA literature, both the boundary condition you will find. Periodic boundary condition is more popular, but open is also very popular. And open has, as I've said, several variations. Several variations in you'll find in case of open boundary condition. So next we are going to present a transition diagram, a diagram that is used to characterize a finite cellular automaton. See, in case of finite cellular automaton, we always have finitely many configurations, right? Finite cells, so obviously it is having finitely many configurations. So it can behave like a finite state machine. In some C literature, sometimes finite cellular automata, they are termed as, they are named as a special class of finite state machine. Although cellular automata, they are not finite state machine, they cannot be. But since here, it is actually finite number of configurations you have, and you have a G, so it is a finite state machine. Sometimes someone considers it as a finite state machine. So the definition of transition diagram. Transition diagram is a diagram that represents predecessor successor relationship of all configurations. So now, since you have finite number of configurations, you can draw, at least theoretically, you can draw all the configurations. So if enough paper and pencil given to you, and you can draw all the configurations, and then who is the predecessor of a given configuration you can find, and who is the successor, that also you can find. So now on a paper, if you draw the diagram, right, then that diagram is called transition diagram. Sometimes we call it configuration transition diagram. So from one configuration, the CA is moving to which configuration, that is specified by that diagram. So take an example. Suppose we have say n equal to 3 only. We have only 3 cells we have. For simplicity, I have considered here only 3 cells. And suppose is equal to 0, 1, 2. Right? And so r equal to 1 means nearest neighbor. Okay. And my boundary condition is periodic. Right? So this I have assumed. Okay. So now I have to specify the rule. Okay. So I'm going to present you two configuration transition diagram. So A is one rule, B is another rule. So there are two figures. And see, in the rule, how I've presented the rule, the old format, the old first format, in tabular format actually. Okay, the leftmost, the sorry, NSB actually, it is 000, then 001, and the rightmost is here it is 222, right? Because it has in the domain you have this one 000, 001, so up to 222, right? So in the domain you have 2 to the power 3, actually 27 values. So 27 elements in the domain. So against that I have written the rule. Please recall the last class. Last class we have discussed the tabular format. Okay. So sometimes we represent the rule in decimal format, but here I have represented in this way. Okay. And the diagram, what does this diagram mean? So there are some circles. In the circle, some decimal numbers I have written. Right? These decimal numbers, they these decimal numbers are actually the configuration and decimal representation of the configuration, right? It is written in this code. Now observe that I have taken only n equal to 3, right? And how many states are there? Here also 3. So how many configurations possible? It is always 3 to the power 3. In general, if you have n cells and say k number of states, and n cells, right? So how many configurations you'll find, you'll get, that is k to the power n, right? Simple, k to the power n. Here k is equal to 3 and n equal to 3. So in both the cases, number of configurations, they are 27. Now see what I'm getting out of here. Last class we talked about space-time diagram. Space-time diagram is also a useful tool to understand the dynamical behavior of an automaton. This is another diagram which tells us dynamical behavior. What I'm getting out of here, see, consider rightmost figure. See, all the configurations, they form a cycle. They are in some cycle. And 1, 2, 3, 4, 5 cycles are there. Okay. So, and from one configuration is reached, can be reached from another configuration only. So that interesting behavior you can see just looking at the figure. Whereas on the hand side, what I'm getting here, first of all, I'm getting a remarkable difference. All the configurations, they are not in cycle, right? All the configurations are not in cycles. There are some configurations. For example, you look at the so some circle in the rightmost side. So 11 has no predecessor, right? 11 has no predecessor. So from this figure, you understand 11 cannot be reached from anywhere, right? Similarly, 21, 25, 17, 7, they cannot be reached from anywhere, right? So they are the configurations, but they can never be touched from any other configuration, right? Similarly, I mean, on the other hand, there are some configurations, say 24. In the 11, say, look at the 24. A circle, 24, it is reachable from three configurations. I mean, it has three predecessors actually. So look at, so 24, its one predecessor is 2, another is 23, another is 3. So 24 is another a configuration, you know, what from which is reached, which can be reached from these three states, these three configurations. So you are getting here a flavor of many to one mapping. Ultimate is a CA, it's a map. So in the domain value, if you write say 3, 23, and 2, and codomain if it's 24, so for the G maps 3, 23, and 2 to 24. So in the second picture, in the second figure, we are having these kind of things. Whereas on the left figure, we always see some kind of one-to-one mapping is there. So this is the beauty of transition diagram. When n is small and number of states is not huge, then transition diagram is the best way to represent, to show the dynamical behavior of a cellular automaton, right? And obviously we understand, for example, for say if n is high, say, and say k equal to, see here is equal to 3, and consider say n equal to 20, and so you'll have 3 to the power 20 number of states is configurations. It's practically not feasible to uh, to note down all the configurations, but for the small n is very effective. So, as I've said, a transition diagram gives us a detailed picture of dynamical behavior, the CA, and obviously it helps to characterize a finite CA. We shall see when we especially discuss about cellular automata as technology, uh, and then we shall use this diagram to understand the dynamical behavior of a cellular automaton. So now we are moving to another special class of cellular automata called linear cellular automata. We are starting this linear cellular automata under the finite cellular automata, but it does not mean that linear cellular automata they are always finite. However, in the most of the works done in the domain of cellular automata, in the domain of linear cellular automata, they have considered that cellular automata, cellular automaton is a finite one. So I am discussing here. But the points which I am presenting here, so all are applicable to uh, to the inverse also. So first of all, when you say a CA linear, a CA is linear if its global transition function is linear. It's a linear map, right? By the term linear here, we are not referring to the line. We're saying that the map is linear. And in case of, although J is a quadruple, but from that quadruple we get a global transition function called G. So if G is linear, then we call a CA is linear. Now, when we call that a function is linear, so let us consider two vector space W and V over a field K. Okay. So we are considering the linear function. So let us consider two vector space W and V over a field K. Right? Now we call a function f from W to V is linear if the two conditions are satisfied. These are additivity and homogeneity. So if the function is additive and if the function is homogeneous with degree 1, then the map is called a linear map. Right? Now, what is the meaning of additivity? Additivity is very simple, obvious. It's an additive one. If x plus y equal to fx plus fy for all xy, if this condition is satisfied, then f is additive. Okay. And what is homogeneous? Here, homogeneity of degree 1. So, homogeneity of degree 1, it means f of alpha x, alpha is a scalar here, x and y, they are vectors because W is a vector space. So, all the elements of W, they are vectors. But alpha is a scalar. Okay, alpha is an element of K. K is a field, right? And if if of alpha x equal to alpha into fx, if this condition is satisfied, it is homogeneous with degree 1. So actually homogeneous means, so actually it is f of alpha x equal to alpha to the power say k dot k into fx. So it is the general meaning of homogeneity. But degree 1 means that k, the power is 1 actually. Okay. So to be linear, homogeneous is not the only one. It has to be homogeneous, but its degree is to be 1. So it's homogeneous with degree 1. So f of alpha x is to be equal to alpha of fx. Now if these two conditions are satisfied by a function f, we call that function as linear. So now to be CA as linear, so these two conditions have to be satisfied by G, the global transition function, right? And before that, the configuration space is to be considered as a vector space. So we can do that one. Okay, you have the state set and vector space. So configuration is a vector space over that's S, the state set. Right? If I consider that one, and then if these two functions and then these two conditions are satisfied by a rule, by the global transition function capital G, then the CA is called a linear CA. Now, what is the relation between this linearity of CA and the function? It's this theorem states that one. A CA LSMR is linear if and only if R is linear. That is, if the rule is linear, then the CA is also linear, and vice versa. If the CA is linear, right, then its rule is also linear. Okay. Now come to the proof. Proof is simple, interesting also. So assume that G is linear, right? Then let us consider, two-state sequence, say S1 Sm, right, and S1 dash Sm dash. What are they? Consider a cell I of the lattice. Consider a cell I. So it has m neighbors. Cell I has m neighbors. Suppose S1, S2, Sm, this is the state sequence of these M neighbors. And of the same M neighbors, the other state sequence is S1 dash, S2 dash, and Sm dash. Right? So these are two state sequences. I mean, or say, I should say that the states assigned to neighbors of a cell I. Right? Now, considering this, I want to perform this operation R of S1 Sm plus uh, S1 dash Sm dash. If it is so, from this I can write this step. It is actually nothing but global function g of c and c dash, where c is assumed, where c is a configuration for which the I can get the state S1, S2, Sm of the cell against the cell I, and C dash is another configuration against which I can get the state sequence S1 dash, S2 dash, Sm dash for that cell I, same cell I. So from that I can write, so G equal to G of C plus C dash. Now G is linear. So linear means from the additivity condition I can write here G of C plus G of C dash, and restriction always I am putting over I, putting on I can write because G is linear. What does it mean actually? It means R of S1 Sm plus R of S1 dash Sm dash, because G of C on I, it means R of actually S1 S2 Sm that I've assumed, right? Similarly, G of C dash is means R of S1 dash, S2 dash, and Sm dash, and that's all. So this shows if G is linear, then R satisfies the additivity property. First property satisfied. So the next one is I have to show that it is homogeneous with degree 1. Now consider alpha is a scalar, right? And alpha is state actually here, right? So let us find out, like similar way, alpha into R of S1 dot Sm. Now it is equal to actually alpha into G of C over I, right? Now since G is linear, I can write this one using the second property of the function equal to G of alpha into C for restriction number I, and it means this one, right? It means that R of alpha dot, multiplied by this S1 Sm. So there's a mistake. Its I is not required here. I have written here. It's a mistake. So don't consider the last bar and I. Anyway, so what I get from alpha dot R of S1 Sm, I get R of alpha dot S1 Sm. So the second property is also satisfied. It means if G is linear, then R is also linear. Now to prove the theorem, I need to prove the next, the reverse one. Reverse one is assume that R is linear. The reverse one, R is linear. Okay. Now then, if R is linear, then you show that G is also linear, and it can be shown the reverse way actually. What I've shown, uh, uh, then you have to consider here the last point actually. Okay. From that you have to show that G is also linear. So you do it. It was a task. You do it. You test if it's linear. When R is linear, whether you can see, you can get that G is also linear. Okay. So in this way, I can get that R is linear, G is linear. What I get, if G is linear, then R is linear. If R is linear, then G is linear. So hence the proof. So it is the proof of the theorem. So therefore, to see if whether a CA is linear or not, we need to test only whether R is linear or not. Right? And what is the advantage of considering this linear cellular automata? Advantage is you will have a support of matrix algebra and vector space. That algebra, linear algebra, will have support of linear algebra to characterize the cellular automata. So we shall see later that if a finite CA is linear, then the CA can be represented efficiently by a matrix. And once you can represent it in the matrix, so we have many known properties of matrices, right? That can be applied, that can be used to characterize the CA. So this is the reason why many people are interested on linear CA. On the other hand, if the CA is not linear, if it is non-linear, for example, we don't have much tool to characterize their behavior. We can see, we can plot their dynamical behavior using space-time diagram or transition diagram, but their theoretical property, their mathematical property, difficult to achieve. Difficult to discover. So, linear cellular automata are interest of researchers. So, we'll discuss this part, the calculation tool, and how to use linear cellular automata uh, uh, in coming classes. So today up to this. Any question you have?
I just want to have a question that if alpha into relay R of S1 to Sm and relay R of alpha into S1 to Sm is similar. Is it associated?
Sorry. Please repeat.
Alpha into R of S1 to Sm and
Right.
the last statement, which is like relation of alpha into S1 to Sm. Are they both similar?
Yes.
Okay.
Similar means I'm deriving it from that one.
Okay.
Sir, I think if you can give one example of linear scale, maybe an ACA, then it will be more useful.
Sorry.
If you give one example of linear CA and how it works, like given at least one ECA which is linear, then it will be probably more understandable to them.
Okay. Should I do that one? So if it is so, then
Yeah, it's like
then I have to use the board. Okay. So I'm stopping the presentation. Okay. Just a second. Can you see my board? So, so what is the question that how a function is linear? So take an example. The Parijat, what is the question? Whether that part is needed?
Uh, well, no, I mean, what I was asking is like, if alpha of a relation, the whole S1 to Sm's relation is similar to the relation R of alpha into S1 to Sm, which was like the for the proof of the homogeneity, the first statement and the last statement. I was saying, I mean, are they both are equal? That was I was asking. You said
Okay.
yes.
That I have derived. Anyway, say uh, uh, consider an ECA rule. Say rule 90. Say ECA 90. What was 90? It was 000 0100 11 100 101 110 and 111. In case of 90 it was I'm having 0 1 0 1 1 1 0 1 0. This is the 90. Last class you have seen it. Is the rule 90. So this one I can get actual rule. It is actually if I consider it is x, it is y, it is z. So then actually 90 is actually rule 90 is actually x or z. Actually it is x plus z mod 2. This is the meaning of x, sir. So here, so is the rule 90 is linear? First condition is it's a modular thing is here. Okay. So you understand this is a modular one. Sorry, is a addition one. And this addition tells us that okay, uh, it will be a linear one. Monica, what kind of question you are asking? What to show?
So those two properties are satisfied by this.
By ECA 90, na?
Yeah,
So
yeah.
in case of ECA 90, say say consider say one configuration 0 1 1 0, so n equal to 4. N equal to 4, it is 0 1 1 0. What is the next configuration? Or what is the next configuration here? So if I consider periodic boundary condition, it will be 0 0 1, it will be 1, and it is 0 1 1, it is 1 1 1 0, it is 1, here it is 1 1 0, and 1 0 0 4, it will again be 1. Okay, so next consider, so this one say it is x, so I'm considering this is the x. Okay, now y is equal to 0 0 1 0. Okay, then what I get, it is 0 0 0 1 is 1, it is 0 1 0 is 0, and then 1 0 0 is 1. Okay, so that I get. Okay, let me remove this part. So this is x and this is gx, this is gx, and this is gy. Now if it is linear, to be linear, two conditions, additivity and homogeneity. So additivity condition means, so gx plus y, it is to be gx plus y. Let us see whether it is happening or not. g of x plus y. So find first x plus y. This is actually 0, 1, 1, 0 and 0, 0, 1, 0. Here addition is modulo 2 addition, right? So this is 0, 0, 0, 1, 0. This is actually x plus y here. I am getting this is x plus y. So that I am getting here. So x plus y this. Now g of x plus y is equal to g of this one, right? G of this one. So what is the g of this one? Say 0, 0, 0, 1. 0, 0, 1 is 1. 0, 1, 0 it is 0. 1, 0, 0 is 1. This is the g of x plus 1. Okay, you can find from the table also. Okay, that I get in one side. So here g of x plus y is this one. 1, 0, 1, 0. Oh, now test whether it is equal to g of x plus g of y. Sorry. So what is gx? Gx is already I have done 1, 1, 1, 1, and gy is equal to 0, 1, 0, 1, and do addition 1, 1, 0, this 1, this 0, this 1. So I am getting gx plus gy 1, 0, 1, 1, and check both are same. Okay, it is g of x plus y and gx plus gy. This is 1, 0, 1, 0. Right? So first condition is satisfied, and you can test. So I have given one example. You test arbitrary x and arbitrary y. So always you will find this one. This property is satisfied. So it shows it is additive. First thing is it is additive. Additivity is the first condition, but not the only one. Additivity is the first condition, but not the only one. Then next condition is next condition is the homogeneity, right? And homogeneity means here what was the alpha g of alpha into x is equal to alpha alpha of gx, where alpha is either 0 or 1, right? Suppose alpha is 0, right? So if alpha equal to 0, then g 0 into x is equal to 0 into gx. For any x, 0 into x is 0, right? For any x, 0 into x is 0. So this is 0, and 0 into gx is always 0. So taking alpha as 0 is useless because it is always satisfied. I mean, it is always satisfied. Now if alpha equal to 1, then what I get? The similar thing. 1 into x is equal to 1 into g into x is always true. 1 into x is x, and 1 is gx is gx. So alpha equal to 0 and alpha equal to 1, this condition always satisfied. The same condition. It is always homogeneous. Okay, this is true for any binary CA. Right? Any binary CA, homogeneous condition is redundant. Right? If you have two states only, homogeneity condition is redundant. So therefore, if a CA is additive, then the CA is linear. So I have shown already that rule 90 on the ECA 90 is additive one. So, and this by default, this is homogeneous. So therefore, the ECA 90 is ECA 90 is additive one, right? ECA 90 is additive one. So ECA 90 is additive. Additive PIV, additive or linear, because they have same meaning actually. Same meaning. If it is additive, then it is linear. Right. So how many rules are there to be additive? There are how many rules in case of ECA? How many is possible? There are only 8 rules. 8 rules possible, which are linear. How I am getting 8 rule? How I am getting a 8 rule? It's obvious actually. Say here my function, my rule is x, y, z. So activity says it will be x plus y plus z. So there are 3 options, or sometimes I can get x plus y, sometimes I can get x plus z. So how many options I can get? So 2 to the power 3. So 2 to the power 3 options are there. So I can get 2 to the power 3 rules as linear rules. So in case of ECA, only 8 rules are there which are linear. Right. So like rule 0, rule 90, rule 60, rule 150. These are the linear rules. Yeah. Any more question? Any question? Monica, is it okay or no?
Yeah, it is okay. Sir, is additivity always implies linearity in case of
Yes.
non-binary case?
Additive. Sorry. No. 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 No.
Additivity,
No. 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 No.
non-binary case.
No. For non-binary, say you have to test the additivity one. For the homogeneity, you have to test. But in case of binary, say it's redundant. Yes. Or maybe I have started with rule 90. So should I show that rule 90 is also linear rule? Should I show x, y, z? This is x plus z or x XOR z. This is also a linear rule. What are the condition of linearity? X plus y. Okay. So let me write. Should I show it again? Say 90.
No, it is.
It's okay. So if I take two vector, so instead of x y that I have used here, so u and v. Say u and v. Say u plus v is to be 90 u plus 90 v. So this u is actually this one. So you take any one, say 90, you can test, say 0, 0, 1, say plus 1, 1, 0. You can see here it is always 0, 0, 1 plus 9 plus 90, 1, 1, 0. See, this is a vector actually, 3 arguments are there. U means x, y, z actually. Okay, because 90 has 3 arguments, right? So say one argument is a 0, 0, 1. I didn't put here comma. You can put here comma also. So that is 0, 0, 1 plus 1, 1, 0. You can do it. If you do this addition and then you use apply 90, or you do it in the same, first apply 90 over 0, 0, 1 and apply 90 1, 1, 0 over 1, 1, 0, then you add, you'll get the same result. Okay. Any question? Any more question?
Sir, why the additivity property is not supported in non-binary C?
Non-additive property?
Not supported in non-binary C.
Not supported.
No,
That
no,
sir, actually I have the same question. What
So I didn't get your
no,
point.
I am asking the same thing, sir. Actually, for non-binary C, if it is a D state C D greater than 2, so
Hmm.
these two properties can be maintained, additivity and homogeneity.
Yeah. It has to maintain.
Okay, okay. I got this much. Sorry, sir.
I was asking whether additivity will imply homogeneity. That I want to ask.
Okay, okay.
Additivity implies homogeneity in case of binary C. Ah,
Yeah, yeah.
Okay,
okay.
okay.
So if you work with GF2, for example, additivity is sufficient. Okay. Any more question? If no, then I am leaving.